Cool. So my name is Ed. I work on the Eagle team, and we're going to talk about simulation. So we're talking about circuit simulation, and I guess if we just start very basic, we're going to cover a lot of stuff. I'm going to go through what is simulation, starting just from basics, a little bit at a high level. We're not going to go into too much detail about how circuit simulation works, but I'll point out a couple things there. Or a couple of resources where you could get more information. We'll talk about how we have implemented it in Eagle and how you go about simulating your schematics and creating new schematics that are ready for simulation. Also, how you do this in a library, how you create parts that are ready for simulation within a library. Also, how you do it just within a schematic. Maybe you're not creating library parts. You just want to simulate something quickly. You can do it right in the schematic. So we'll go through that, and we'll look at some of the other features that Eagle offers along the lines of simulation. So let's start. And so what is simulation? So basically, simulation is a way for you to simulating your circuit with a SPICE-based simulator, which is what we do in Eagle, is a way for you to pre-calculate how your circuit is going to act. So it may be, as we posted in the summary for the webinar, it may be something as simple as verifying the current through a diode, or it may be, an advanced sensitive circuit design, maybe an amplifier, a filter, whatever it is. Something very carefully done, by hand, and maybe you want to verify it before you actually go and build it. Circuit simulators came about a long time ago, many years ago, I believe late 70s, back in the EECS department of UC Berkeley. So that basic engine called SPICE has been used for since then, and in literally hundreds of different simulators. They're all sort of based on all the general purpose circuit simulators are essentially derivatives of the original SPICE program. So what we have done in Eagle is integrate NGSpice, which is an open source derivative of the SPICE simulator. NGSpice is essentially the most recent and stable version of SPICE, with all the bugs fixed and a lot of enhancements and improvements. So it's a really great and powerful simulator, and we have integrated it. It comes with Eagle, so as soon as you install Eagle, it's there for you to use. So you might be wondering, how does SPICE or how does simulation work? If I have a circuit, let's say I'm just going to open a very basic example. Let's see here. A very simple example of a very basic circuit that we can explain very simply. So this circuit, for example, has a symbol of a voltage source. So let's say something like a battery has a symbol of a resistor and a diode, and essentially this circuit will allow current to flow from the battery through the resistor and through the diode. And if this is a light emitting diode, an LED, as it is noted in this schematic or notated, then this LED would give off light. And so that's the reason for the style of that diode symbol. So if you have a circuit like this, or if you're making a circuit like this, you may want to simulate it and see what happens to the current or the voltage in your circuit under different circumstances, under different voltages, maybe under or with an input voltage that varies over time, let's say. So simulation is how you would perform this sort of pre-validation, this pre-calculation, to verify what you think is going to happen is actually going to happen. So I'll take a step back for a minute and just say, so with simulation, we're going to go through how to make your schematics ready, how to make parts, how to map SPICE models to your parts, which I'll explain. but to start with, I'll mention that Eagle ships with a couple resources to get started with simulation. Some parts that are pre-configured, ready to go right out of the box. And one of those libraries is called NGSpice Simulation. I'm just going to open this library here. And just sort of toggling through some of the parts, you can see in this library there are diodes, here's a resistor, this is an inductor, we have voltage sources. So a bunch of different parts that allow you to build up circuits ready for simulation. So if you're going to simulate, let's say, a bunch of different LEDs in some configuration with some sort of input stimulus to turn them all on, you would probably come to this library to grab some voltage sources, resistors, diodes, and other parts. There are also controlled and dependent sources that may not mean anything to someone seeing this for the first time. But as I mentioned, we'll point to more resources later. Essentially, there are some parts that when you simulate them, you can specify their value directly, and other parts you can specify their value in relation to some other variable. So let's say I want to have a battery that has 5 volts. You can certainly place that type of part. You can also place a part, let's say, like this part is a current-controlled current source. So that means I'm going to place a part that provides current, but its value is based on another current. Now that's kind of an advanced part if you're a beginner, but just noting that some of these parts are here. There are of course also here bipolar transistors, also CMOS transistors here labeled FET N and P type. And a couple other things. Transformer, there's an op amp, symbol, and ammeter. So a couple things here. Now, of course, these are not the only parts you can use. You can use essentially any part. You just have to make it ready for simulation. And we're going to take a look at how that's done. So there is this library. This library was introduced when we first rolled out simulation with Eagle. And it's essentially now contains all analog parts. So everything that you see in the NGSpice Simulation library, these are typically used to make pure analog circuits. And we'll go through another library called NGSpice Digital, which is actually not public yet, so you can't see it in the managed libraries yet. It's kind of a preview. I think we mentioned that somewhere in the webinar, but it'll be out very soon, and you'll see that it's a new library called NGSpice Digital, and we're going to talk about how we now support digital simulations as well as mixed mode simulations. So that's a good point to maybe take a step back and just talk about the types of simulation very quickly. So let's say I have this circuit here. Now, the types of simulation that we support, and we'll take a look at the simulation command and its related user interface in a little bit. Actually, I'll just open it now. So let's say there's a new command called simulation, okay? And on this main screen, this is kind of the main user interface for setting up your simulation. So I have this circuit here, and I want to simulate it, and I'm just going to go through the different types of simulation that we support. So the first type is an operating point simulation. So this type means I want to simulate the circuit and just see what are the currents and voltages when I power it up. So just time zero, what does everything look like? Let's say I hook up let's say this is a battery, and I hook it up to this resistor and this diode. As soon as I hook it up, what are those voltages and currents? We'll perform one of those in a minute. Actually, maybe I'll just run it right now. So from this configuration tab, four different main types here in this simulation type section. I chose operating point and I just clicked simulate. And what we're going to see is that the output of the simulator, straight from the simulator, is put in this tab here called output. And on the circuit for this type of simulation in operating point, you'll actually see those currents and voltages, okay? So they're showing up here as labels, and I'm just moving them around so they're not sort of in the way. But what this says is essentially this number is very, very small. It means there's essentially zero current flowing at time zero. This voltage is zero, and I'll explain why that is. And then there's a voltage here that's essentially zero as well. These numbers are very, very, very small numbers. They come right from the simulator, and they're not sort of truncated or rounded off. So this 2.3 times 10 to the negative 33, for all practical purposes and for this sort of context, this is essentially zero current. So what I can do here is mention that, so we saw zero voltage, we essentially see zero current. So is that wrong? No, it's not wrong. It's just that the way that this voltage source is set up, it's not really acting like a battery acts. In fact, it's set up as a sine wave source, something that varies its voltage over time. What we can do is for this type of part that is specified as a voltage source, which I'll explain in a little bit, there's a special type of command and related interface to set it up. And in this case, it's called analog source setup. And what I can see here is that voltage source was set up with a DC value of 0 volts. This essentially means if we think of it as a battery, it's a battery with 0 volts. So that's not really what we want if we wanted to simulate hooking up a battery to these components. So of course, under this you'll see, or sorry, I don't want to skip over these other parameters, which say the AC value for this part, if we were doing a simulation over frequency, which we'll talk about in a minute, you would have you may want an AC value here, which is used for that type of simulation. The transient function is used in a transient simulation, which is a time simulation. So over time, if I wanted this component to vary with, for example, these functions, I could choose these here and specify their parameters. For now, we're looking at this very simple circuit and this very simple part. And I just want to say, okay, let's say this is a 3-volt battery, okay? So I'm going to change this analog voltage source to 3 volts. Now I'm going to go ahead and simulate again. And we're going to see something different. I'm just moving this current down. This is the current flowing through this source, okay? Actually, I'll put it here. The voltage at this node on this net called Vin is 3 volts. And we see a voltage over on the diode of about 0.7 volts. And there is some current flowing, let's say 2.2 milliamps. So this current is, of course, controlled by the voltage source and the diode and the resistor values and the types of parts they are. And this is all the result of sending this schematic and this circuit to the simulator and getting the result. So this is a very basic example where we took this basic circuit. In fact, we didn't like how one of the components was set up, so we went and reconfigured this voltage source labeled V1 here. We modeled it more as a battery with just a straight what's called a DC voltage. So it doesn't vary over time, and we simulated and checked the voltage and the current. So this is a very useful simulation, and this is just, as I said, when you power your circuit, what happens right off the bat. So that was an operating point simulation. Let's go ahead and take a look at a transient simulation. Transient is over time. So if I want to see my circuit, how it changes over time, I choose transient here, and I set up the start and stop time. Since I'm on this panel here, I'll mention that So we've been talking about the left side, simulation type, and I didn't mention the stuff on the right. So on the right are accuracy and stability and precision related parameters. These are sort of the advanced parameters. And if you want to know more about those, the best place to see a really full detailed description of those is in fact in the simulator manual itself. So in your Eagle installation, there is a folder where you can find the simulation manual. I believe it's under documents. We can go take a look over here. In the control panel. And actually, I don't know where it went. Let's just skip that for now. We'll get back to it later. So let's go back to our circuit. We had this diode circuit open, and we did an operating point simulation. I'll point out a couple more things about this panel here. So on the right, accuracy, precision, sort of advanced parameters that you essentially don't ever need to change unless you have a specific reason to. So what you may typically do is just open the simulation dialog, and I'll get back to how to do that in a second. And just sort of leave all these parameters on the right as is, and on the left is where we're setting up our basic parameters. So operating point, notice that when we ran the operating point, there was no plot. There was only a text-based output. I'll just run it again real quick. Click simulate there. So this is essentially the output, and these values are then placed onto the schematic so that you can see them sort of maybe more clearly and in context. There is no plot for an operating point type simulation, but there is a plot for these other types. So we'll look at that in a minute. Anything else here? So at the bottom on this panel, there are a couple fields for number of points. The default values are generally good, and you in general don't need to change those. But what they mean is that this first one here, number of points, let's say 500, it's what I tell the simulator I want to simulate and give me about a granularity of, let's say, 500 points. So for example, if you were on a scope, or if you were testing a real circuit, there would be, say, 500 data points on the screen. That's what that refers to. Now the simulator itself might use more points. That's just how it works. As it's doing its mathematical computations, it may require a few more points to converge, etc. So that's what this second field is for. So I say, let's say, let's say I enter here 500 points. That's sort of my request to the simulator, and it might turn out to be 510 points, and that's perfectly fine. But I put a limit here, max number of points. I might want to put a limit there, and there's already a default value, so that if the simulator requires 10,000 points, I actually don't want to plot that much data. And so this number of points, this second max number of points field, this is where you can say, okay, no matter what you have simulated, I'm going to filter that down into, or squeeze it into, this many points at most. And that's a good idea, because if you have a lot of signals to plot and a lot of data, it can make your plotting very slow. So that's just a function of whatever computer, whatever system you're on. If you have let's say 1 million data points, that's going to be a lot of data to process. So it's a good idea to use something around, let's say, 500, and usually I use something like 1,000 for the max number of points. Okay, so on this panel, we choose our simulation type, and in general, typical case, you don't really change anything else. You might change the temperature for a certain type of simulation, but in this case, we're going to leave everything as is. So the last thing we did was set up a time simulation. I'm going to close this window just for a minute, and I'm going to come back. Sorry, I should mention that, I think I did, but I'll mention again, just feel free to post any questions. Jorge, interrupt me, if anything comes in that you want me to address right away. We'll leave some time at the end, of course. But I just wanted to mention that because I can't see right now the chat screen. So just let me know. Otherwise, I'll just continue. So we want to do a time simulation. So the first thing I'm going to do is make sure that I have something in my circuit that's actually varying in time. And of course, if you're performing a time simulation, you probably, you already have something in mind that you want to look at. In this case, I'm going to keep this very simple circuit, resistor, diode, and voltage source, but I'm going to change the voltage source now to have a 0 volt DC value, but over time, I'm going to add a sine wave function, okay? So let's say my amplitude is 3 volts. It's kind of large. I don't know, let's say 1.5 volts. And my frequency is 1 kilohertz. Actually, let's just do 3 volts, 1 kilohertz frequency. So I'm going to have a sine wave at 1 kilohertz and with a 3 volt amplitude, no offset. I'm going to set the value there, and I'm just going to, I'm going to open my simulation configuration here. And just to back up, I'm typing simulation in the command line. There is also this button here that says simulate. This bar here with these various buttons, these are all simulation related. So the first one is to open up that main simulation window. The second one is for the operating point simulation results. You can turn them on and off, as you can see here. And these are voltage probes. Sorry, this is a voltage probe. This is a phase probe, which we'll talk about. This is an add model button that has to do with mapping SPICE models to your parts, which we'll talk about in a minute. There's digital source setup and analog source setup. And we've already used the analog source setup on this part here, which I just am accessing the same command, but by right-clicking. And only right-clicking on a part that's set up in the right way can show that menu. So I'll mention what that means. You can see that if I right-click on the resistor, there's no source setup because it's not, as far as the simulator is concerned, the resistor is not a voltage source. Okay, so opening the simulation panel again, and we're going to go through a time simulation. So this is transient. I'm going to start at, let's say, time 0, and I'm going to go until, let's say, about 8 milliseconds. There's a note at the bottom here that it's very flexible in terms of what types of values you can enter. Some people like to enter, in scientific notation, let's say 8 times 10 to the negative third seconds, which is 8 milliseconds. Some people like to write 8M. Some people like to write 8ms. The point of this note at the bottom is that you can use these multipliers and these unit characters as you like. You can also use scientific notation. So let's say 0 to 8 milliseconds, we're going to simulate this circuit. I now have a plot, and that's because of the type of simulation that I'm running. So in this simulation results, let me take a step back. So all simulations, as soon as you open the simulation configuration dialog, or this simulation dialog, the first tab is configuration, but the second tab is a netlist. Now you may know what a netlist is. If you're new to simulation, you may not. The netlist is essentially a text representation of your schematic. And for simulation purposes, the netlist is the input to the simulator. So you don't need to create this netlist yourself. In fact, every time you open this window, the netlist is created from scratch from the schematic. You can also click this button here on this first tab, this configuration tab, to update the netlist and essentially generate one again from schematic. And the reason you have this button here is because, in fact, you can make changes to the netlist manually. Let's put it under the category of, let's say, advanced usage. But let's say one thing that I think that's probably clear to all the listeners is that, for example, let's say I have my circuit here, my voltage, my resistor, my diode. Well, maybe I want to very quickly change my resistor value from 1K to 2K. If I know, if I know which line is the right one, of course you have to sort of understand what the netlist is in the format and how it is written. And I'll mention a resource for that in a bit. If you know what you're doing, essentially, you can go in and I can see here that this R1, this actually R underscore R1, that corresponds to my resistor R1 here on my schematic. And I can see that the value was 1K, just like it is in the schematic, but I can quickly, without changing the schematic, I can quickly here just change this to, let's say, 3K. And if I simulate from this tab, from this netlist tab, then it will take into account my manual changes that I've made. And this is a very powerful way to make changes to values in your circuit, without having to close everything and go back and change the part value and all that sort of thing. So maybe I know that my perfect value is somewhere between 1 and 3 kilo ohm, but I don't know what the right value is, and I can just sort of iterate here and make changes and simulate. So let's go back to our plot. So I set up my time varying source, remember. Actually, this label in that place is a little bit annoying. I'm just going to move it. Okay, so we set up our simulation for 8 milliseconds. And we have, if you remember, our voltage source here that was set up to be time varying. And so now we want to see the result. So on the plot, which comes with, again, transient AC and DC type simulations, first thing I want to do here is just zoom in. So as you mouse over on the plot, you'll see that the legend on the right will show the values of all the signals. And the curve that you're closest to will also highlight. I'm going to click and drag to zoom in on a specific part of the plot, and you can double click to zoom back out. So I'm going to zoom in here, and I have essentially 3 signals, and let's see why that is. So on the schematic, I have named two nodes, V in and V out. There's also an independent voltage source is what this part is called. And so I'm going to see the voltages for those named nodes, these named nets here. And I'm also going to see the current through this source, and that's just added automatically. Now this brings us to probes, because what happens is the simulator will plot, Eagle will plot all of the values all of the signals for the named nodes in your circuit. Now in this case, it's very simple, and there are only 2 named nodes, so it's going to show those. It's always also going to show the current through these types of sources. Now you may have a circuit with 100 different named nodes, though, so you don't want to, and you may not want to display all of them. So what you do is go to the simulation toolbar here and add a probe. When you add a probe, it will only look for probes. These currents for the independent sources will still be added, but you won't have the 100 named nodes for voltages. Let's say you'll have only one. You'll have your the one that you put the probe on. So I'm just rerunning my time simulation, and I'm just showing that on the right, and in the plot and in the plot legend, you'll see only 2 signals. So, and sorry if I'm going quickly, I'm going to delete that probe. If you want to see me do that again, I'll just do it real quick. It's called voltage probe. It's in the toolbar here. It sort of acts like an Eagle label. You can see that it's something that you attach to a net here, or a net segment. And it has a name, and the name means, it starts with V, and then the net name is in parentheses, V out in parentheses. That means the voltage of V out. There's also another probe type, which is a phase probe. That's useful for an AC simulation over different frequencies, and we'll take a look at that. So deleting my probe just because I do in fact want to see all named nodes in this case, because I did name them and there's only 2. I'm going to run my time simulation again, and I'm just going to point out for those who recognize this circuit and know what it should do, we can point out what's going on here. So we have V in and V out, and we have the current. Let's go ahead and put our mouse over the plot and see what's going on. I'm just going to resize here. So this dark blue one is the current, and it's showing, apologies. The right side of the plot, this right side y-axis is the current, and voltages are on the left. So as I'm tracing my mouse over this blue signal here, in fact, I'm looking on the right axis, the right y-axis for the values. So what you can see is that although it's inverted, you see that the value at the top here is pretty close to 0. And as we go down on this dark blue plot, you see the value of the current, the magnitude of the current. I'll explain the sign in a minute. The magnitude of the current is increasing. So it's going up to about 2.2 milliamps. These are based on the values in the circuit given to the resistor and the voltages that are seen at the input. So that's what we would expect. So over some time we see V in is this green one. So as V in increases up to here, this green one here, we see this red one, the voltage on the diode, it gets cut off. And at that same time when the voltage at the diode gets cut off, it's about 0.7 volts, the current in the diode starts to flow and increase in value. The value is the current value is negative, but that's only because the convention is that it's coming out of this voltage source. And so the current that we're seeing, I of V1, this voltage source V1, the value being negative just means that it's coming out, it's sourcing the rest of the circuit. So for those who recognize that circuit and understand what it should do, you'll see that this is showing that the circuit will do what it should do. As the voltage goes up, the current will flow through the diode. The voltage will be sort of cut off as much current can flow will flow, and this is a proper operation. So that was a quick simulation over time. While we're here, I'll just show a couple features on the plot. Excuse me. So what you can do is you notice that when I double click, I zoom out. When I click and drag, I zoom in. But there's another operation that allows you to click in one point. I'm going to click at the top of this green portion of the sine wave, and I'm going to move over here, and I'm going to click on another point, single click. And after I do that, it shows me the differences, basically on the x-axis, which we know is time. In this case, I see the difference in time, dx. I also see those specific points that I clicked on. I also see 1 over dx, because in this case, it's useful. 1 over the difference in time, we can think of as a frequency. So in this case, I click the top of those I clicked one portion of a sine wave, and I clicked sort of one period later, and what I see is it's a 1 kilohertz sine wave. And that's correct, because that's how that source was set up in the circuit. The table below will list out all the different signals and their values at those 2 different points that I clicked, and the difference in values for each signal at the 2 points that you clicked. All you do is click essentially anywhere, and that table goes away, and you can do that at any point on the plot. Another feature here is that sometimes in this case it's simple to look at. There are only 3 curves, but if you want to filter what you're looking at, click the sorry, I did that sort of fast. At the bottom here, there's some buttons. dB will turn a dB scale on for the y-axis. Log X and Y, again, like a graphing calculator, that's going to turn on the log scale on the X or Y axis. it's not really appropriate here for the time simulation, but we'll take a look at it in the frequency simulation. And you have this button called signals, which is essentially a signal chooser. What signals do you want to look at? You can also set the range specifically for the X and Y axes as you like. And we'll take a look at the history feature in a minute. So signals, when you click on signals, you get to choose which ones you want to look at. So let's say I'm only interested in looking at V out. I chose clear all first to uncheck all the boxes. Then I chose V out and just click apply changes. So here I see only that signal, and that helps in some cases when you have a lot of signals. Let's go ahead and put V in and V out on. So here we see just those two. Set range, I'll just show it and click apply to skip to get back out. This is, as I mentioned, the X and Y ranges for the axes. You can always reset to get the sort of standard calculation for what they should be, but you can change them as well. And the history feature, this allows you to run multiple simulations and sort of save them, kind of like how a graphing calculator does, where you have multiple memory places to store the data, and then you can recall them later. In this case, same idea. You can say where you want to save. There, in this case, let's say 5 memory locations. Let's say I ran a simulation with a resistor value of 1K, let's say, and I want to save this, all of these signals, all of this data as set 1. I just click save, and it saves it as set 1. And I can recall this later, because I might want to run a simulation, let's say, with a 10K resistor, and maybe I call that resistor 10K, and I save that to set 2. And now I have multiple simulations that I can take a look at, either individually or together, and I can overlap them. And for example, I might want to see one signal, let's say V out, and how it changes when I change some value of some component in the circuit. So this allows you to do that. And I'll show an example of that later with a different circuit. Let's see if there's anything else on the plot. I'll close this here. We looked at that. So I think nothing else to look at right now. Let's go back to the different simulation types. I'm going to open a different example. We're going to go quickly through what an AC simulation is. Let's say this circuit, and just to mention that Eagle ships with these with this example folder under projects examples. You'll see an NGSpice folder. In the release coming out soon, some of these examples have been reorganized a bit. So you'll see what I see here. You'll see an analog folder. These are all the examples that have existed with Eagle from the time that we rolled out simulation. There are also new examples that we're going to go through in a minute for digital, that include digital simulation and mixed mode simulation. So under analog, I'm going to open another example. This one is called RC filter. Again, for those of you who have some understanding of basic circuits, electrical circuits, this sort of a circuit is probably very familiar. And there are resistors and capacitors forming different signal filters. And so what this circuit is intended to do is that over frequency, as frequency changes on this voltage source here, V1, these different components are going to filter out the signal in different ways and at different specific frequencies. I won't talk more about how that works, but we are going to simulate it. So you can see that I have a bunch of components, and I've placed a bunch of probes. In this case, I placed voltage probes, you can see, on these different nodes, and I've also placed phase probes, because what we want to see is how the voltage and the phase changes over frequency. So I'm going to open the simulation command again in the dialog, and you'll see that in this example, it's already pre-configured that AC sweep is the type of simulation we want to run. This is a simulation over frequency, and so like the time simulation, we have a start and an end, but in this case, these are start and end frequencies. So this is set up from 1 Hertz. You can see that you could have typed 1 or 1 Hertz. Either is acceptable. And it goes up to 500 meg. I could also have typed e to the 6, or I could type all the zeros out. I'm going to leave it as 500 times, or 500 E6, which means 500 times 10 to the 6. So 500 megahertz. The type here, there are two types of frequency simulation. One is linear and one is decade. And that just refers to how many points and what sort of intervals you're asking the simulator to run through. In this case, let's say we run a decade type simulation from 1 to 500 megahertz, and we're going to take a look at the output. Excuse me. So here we go, and remember that we have in our circuit, we have a voltage source here. You can see that it does not have a time function like a sine wave or anything. It just has an AC value of 1. For simulating over frequency, many times 1 is used, not because that's the actual signal that you might see in your circuit. For example, a very sensitive hearing aid or something, for example, would have very, very sensitive signals, possibly down into the microvolts or nanovolts. But for simulation purposes, when you use 1, it lets you scale everything in a simple way. So if I simulate, my input as 1 and my output says 10, then I know whatever my input is, the output will be 10 times greater. So 1 is kind of used as a, let's say, a pro tip, just as a simple way to scale your value. So I'll leave it as 1, and we expect that over time, this input signal will actually drop off. So what I'm going to do is use our signal chooser. I'm going to clear everything because we want to take a very careful look at what's going on here. So I have a V out. Let's see, where is V out? V out is my last node, so that's good. And I want to see VCAP 1 and I want to see VCAP 2. In fact, I want to see V in also. So I'm going to choose, excuse me. Let's see. Oh, I have probes here, so I'm not actually plotting V in. That's fine. V in is going to be actually a straight line because its AC value is 1. So let's see VCAP 1, VCAP 2, and V out. Choose those, and you can see that for an AC simulation, the plot is already in a log scale, and on the x-axis, and the phase is on the right y-axis, the second y-axis. But I've filtered out all the phase. So we're looking only at the left side, which is automatically, in this case, plotted in dB values. If you don't know what that means, it's essentially just a calculation that scales the voltages in a way that that has a special meaning. You can turn off dB with this button here, and in that case, this is these values are not scaled. These are the actual voltages. Because it's easier to see, and this is one of the reasons for this dB scaling, I'm going to turn it back on, and I'm going to just point out that there are a few points where you can see that something is happening. At this point here, let's say, what is this, about 1,000 hertz, you can see that all of the signals start getting attenuated or made smaller as frequency increases. At another point here, this is, looks like about 150 kilohertz. And then another point here, we see we see the signals drop off. This is about, what is this, 1.59 megahertz, I believe, or is that 15 point? Yeah, it's about 16 megahertz. So we do see these signals getting attenuated, and you'll see in the notes for this schematic that these values, these resistor and capacitor values, were designed to have 1.5 kilohertz, 159 kilohertz, and 15.9 megahertz cutoff frequencies. If you don't know exactly what that means, again, it's just a function of how this circuit is supposed to work. It's supposed to cut off the signal at those specific frequencies, and that's exactly what we saw. I may skip a DC simulation for now. Let me see if I have a quick example. Yeah, we do have a quick example here. This FET characterization, this is a MOSFET device, field effect transistor. I believe this is set up for a DC simulation. So one of the things that students do when learning circuits and also circuit simulation is to simulate this circuit. This is a kind of a common example in engineering or electrical engineering curriculum. And so that's why it's here. It may be familiar to many of you. So essentially what we're doing is we have a transistor. It's connected to a voltage source and a resistor. There's also another voltage source here on the right side, VDD, and there is an ammeter placed in between to see the current. And essentially this circuit, you can vary the voltages either at this, what we call the gate, or at this side, which going through the resistor is connected to the drain of the transistor. So we can vary the voltages and see what happens, see what the current is. And this is many times considered a MOSFET characterization circuit. So we'll go ahead and open, I already have it open. Open the simulation dialog. You'll see that it's set up as a DC sweep. This means that we're going to sweep a independent source. In this case, the source is called VG. This is the gate voltage. I'm going to sweep it from 0 to 10 volts. Now a DC sweep it's not over time, it's not over frequency. It's essentially at 0 frequency and at 1 time, but we're changing some DC values, and we want to see what the circuit does in response to that. So let's say I'm simulating VG from 0 to 10 volts, and note that I'm keeping this other voltage VDD fixed. And what we're going to see, let me filter out some of these signals. I want to see, let's see VGS, this is the voltage from gate to source. We want to see that increase. We're going to see the current, sorry, not the gate current, because that's essentially 0. We're not so interested in that. But we are interested in the drain current, or the current going through the source VDD. Remember that I said that the currents are shown as negative when they come out of a source, out of the positive pin of an independent source like this. I just didn't want to see them as negative, so I placed an ammeter in here, which is pointed in the correct way. And so I'm going to look at the current V cur 1, which is my ammeter, so that I can see the currents actually increase, which kind of feels a little more intuitive. So the red line here goes along with the x-axis. This is the voltage that I'm sweeping. So it's increasing from, if we look at the x-axis, 0 to 10 volts. The value here in kind of a greenish color is the drain voltage above, well, let's see, where is that? Yeah, that's actually on the drain of the transistor. And this purple one is the current. So essentially what we see is as we increase the gate voltage, this red, we see the current of the transistor going from drain to source increase and increase in this specific way very quickly, and then sort of taper off. I won't say much more about that for now, but that is the expected result. So let me back up. We went through, I wanted to go through those examples just so you saw them. Transient time over time simulation, an AC simulation over frequency, and a DC simulation. We also did an operating point simulation. So now you're probably wondering, well, how do you get started? How do you what parts do you use? How do you make your schematic simulatable? So there is in fact a example just for that purpose to show you how you make your circuit ready for simulation. So here's an example of the same circuit we've been looking at, the diode example, but this is a copy of that circuit, and in fact these parts have been just taken from available libraries. Let's say a couple of them probably. I'll look at the info. This resistor came from the library called Resistor. This diode came from the library called LED-LumiLED, and this this battery symbol here came from a library called Battery. I believe these are all available, public shared parts that you can all you can all download. So the point here is that this circuit has not been made ready for simulation, and we're going to make it ready. And you know it's not ready because as soon as I run simulation, it says unmapped models found. All components must be mapped to an intrinsic model or a SPICE subcircuit prior to simulation. Before simulating, be sure to map your components from the add model dialog. So a lot of text, but essentially it means you cannot simulate yet. How you make this ready is using the add model command. So what I like to do is select all the parts in the schematic, right click on one of them and click add model. Actually, in this case, it's telling me, sorry, that this circuit was part of what came with the examples and it's not writable. What you have to do is just copy all the files from the example you want to look at, copy it to another directory. I've already done that here. So this is the same example. So select everything, right click, choose add model. And the first thing it's going to do is look for any ground nodes. This is something a little peculiar we can discuss later if needed, but essentially all circuits that you simulate with a SPICE-based simulator have to have what they call a ground node. Its name is node 0. It's sounds kind of cryptic, but essentially it sees that these parts, these are power symbols and they're ground symbols, and they're called ground, GND. There are some smarts built in where Eagle can recognize what looks like a ground symbol actually is a ground symbol, and it wants to know that in fact they are ground symbols. So in this case, I'm going to say yes, these are all ground symbols. That's fine. Make them the SPICE ground node 0. That's fine with me. And that is what you should do in this case. So to add models, what we're doing here is essentially there are 3 types of models. There are intrinsic models. This means that the parts that you place and the parts that you're trying to simulate, the simulator already knows what they are, and you do not need to provide too much, I apologize. The simulator knows what they are intrinsically, and you do not need to provide a model file to simulate them. There are 2 other types of models. One is called a model card in some of the SPICE documentation, and another is called a subcircuit. So a model card is a file that you have to actually supply, and some parts require it. So for example, a resistor, an inductor, a capacitor, these do not require any extra files. They are mapped to intrinsic models, so the simulator already knows what a resistor is. In other words, you just have to tell it what value it has and what the connections are. Similarly for a capacitor, although the capacitor is a little different because sometimes capacitors are polarized, so the order matters in terms of which pin is what, and we'll see that in a minute. So here I have, the last type is subcircuit, which is essentially a black box. You can make any symbol, anything that you want to simulate. Make sure the symbol has some pins, and you can map that symbol to what is called a subcircuit, which then you can define what is in the subcircuit. These models that I'm talking about, these are how the simulators, these are the mechanism for how the simulator knows what your parts mean for simulation and how they should operate. So in this case, what we're doing is we're taking our circuit, we selected everything, and we're kicking off the add model dialog. How this works is it looks at all your components, and it makes a guess in terms of what they are. Some of the guesses may not be correct because it's using essentially the part name to make a guess. In this case, the resistor, the name is R1. It maps to the correct SPICE type, and everything is okay in terms of this SPICE type. This LED, however, it's the wrong type. It thought it was an inductor because SPICE thinks SPICE uses L internally to represent an inductor. It's okay though. We want this flexibility so that we can name our parts however we like, but in this case, naming this part LED does not correctly choose diode as the right type, which is what it should have. So the LED is a light emitting diode, and in fact, I want to choose diode for that type before I move on. this other part is a battery symbol, and it's named G1, which really has no significance for the simulator. And again, it doesn't know what type it is. You might say, well, I wouldn't know based on the description, or on something else. And certainly there are some things done to make some guesses, but these examples are shown to show you that sometimes it can be wrong, and you want to make sure you have the right spice types before you simulate. So in this case, we know it's a voltage source, and we're going to choose voltage independent voltage source. Just means that the value of that source does not depend on anything else. It's a battery. Now here you'll notice that, again, this schematic was not made for simulation. It's not ready for it. And so this voltage source actually has no meaningful value. I can actually change the value right here, and I can just say it's a 10-volt voltage source. The diode doesn't, don't worry about the value here. The resistor also needs a value. I'm going to leave it out though, so you can see that it will check that anyway if I forget here. This dialog is meant to map models to part symbols, not meant to, or it does not care about the values at this point, but it's provided here for convenience. So the next step is, and you can see on the left column done, you can see that the ground symbols are done. These other ones are not, and the reason is because I have not mapped them yet. So if I go to resistor, I click map, and just mentioning that on this load model tab, it says this is an intrinsic device, there's no model needed. So it actually skipped this tab and it went straight here to the map pins tab. What we're doing here is essentially mapping the symbol pins to the model inputs. Since this is all based on what type is chosen in this drop down here. Since this is a resistor, it knows there are two inputs. They're just called N1 and N2. And I'm just going to map the pins 2 and 1 from the symbol to those model inputs N1 and N2. I know that the resistor, it doesn't matter which way I go. I could map 2 to 1 and 1 to 2, or 1 to 1 and 2 to 2. It doesn't matter. There is no polarity on this resistor. So I clicked map and I clicked OK, and the resistor now shows as done. Now you might wonder, what if I have 100 resistors? Well, if you have 100 that are from the same device, so for example, I always place the same type of resistor from the same library, you do one and they'll all be done after that. So don't worry about having to do each one individually, but you do have to do each unique device. For the diode, this is an example of where it is not an intrinsic model that does not require a file. In fact, it is a model card. It is a diode which requires a model card, and you do require a file. So what you would do is go ahead and load a model. We'll talk a little bit about this in the end. I'm sure there'll be questions. But essentially, I'm going to load the right type of model for a diode. I'm going to load a diode model. In your Eagle installation, it does come with some models under examples, Spice examples, and there are some models that you can use. DMod is a basic diode model. I'm going to load that file. It's going to verify and check the file that the file is okay, and I also get a choice of where do I want to save it. I'm going to go ahead and click OK to save in the current directory for this project. I could also choose what is called the global models directory, which is a place where you might want to store models that you use through different projects. I realize we're getting short on time. I'm gonna get speeding through here. So for this diode, I wanted to show this example because if you know what a diode is, you know that it has a anode and a cathode. And in this case, I see the symbol pins are A and C. I know the anode is the plus pin and the cathode is the minus pin. And so I need to choose that here when I say, how does the symbol map to the SPICE model? In this case, A is positive, C is negative. The model is good. I click OK. It's going to verify and everything is OK. The voltage source is just like a resistor. It's very simple. The model input, simple meaning there is no model needed, no file needed. The simulator already knows what it is. It knows that there are two pins called plus and minus, and I know my symbol has plus and minus. So in this case, everything is already OK. I click OK and everything is done. All the boxes are checked green. This schematic is ready for simulation. all I would do is name some nodes, get rid of these default names, V in and V out in this case. I like those names. And now when I run simulation, oh, there we go. R1 did not have a value. I did that on purpose. I'm going to go ahead and run the value command and click the resistor and give it a value. so that you could see that it will also check some other things. In this case, the resistor could not be simulated. So now I open the simulation dialog and everything is okay because there were no error messages. I'm going to simulate time transient from 0 to 10 milliseconds. And we're going to see, this battery, everything's ready to simulate, but this battery or this voltage source did not have anything interesting going on. I'm going to go ahead and set up our 3 volt, 1 kilohertz source again. Let's put a DC value of 0 volts. I'm going to go ahead and, go ahead and run this again. Time simulation from 0 to 10 milliseconds, and we see the same plot as before. Remember that when I started this circuit was just any schematic. This was your schematic, not ready for simulation, and I went through the mapping process and made it ready. I'm going to actually now skip how you do that in a library because it's essentially exactly the same. Go ahead in your library, and when you make a new symbol and you make a new device, you're going to use the same command, add model. You're going to go through the same process, map the model pins to the the symbol pins to the model inputs, and you click save. The difference is that when you do it in a library, everything is saved in the library, including the model, and there is no file where you saw before when I did it for the schematic, there was actually a model file that I chose. Where do I want to save it? Where should it come from? Okay, so there's certainly more on that, how to do it in a library, but I'm going to skip that. Now we're going to go to examples now because we want to preview. I've already shown some analog simulations. I showed the diode. Here's an example of an op-amp. This is an example just showing really quickly. If I go and add model, I use the add model command a lot of times just to see what is already mapped, what kind of model is already mapped. So I go ahead and go to add model and click the map button, and I see here that this is in fact one of those sub-circuit models that we talked about before. A sub-circuit model is basically a circuit netlist inside what is called a sub-circuit. It's certainly advanced to create your own, and we won't cover it here, but this is an example of a circuit that uses one. So in this circuit, this is a op-amp part. It has a sub-circuit model mapped to it. And in fact, in this example, I have one that's mapped from a library, this one X1, where nothing else was done. It was just placed and simulated. And this one, X2, which I actually mapped a new model to. So that's another thing just to point out, that no matter what somebody mapped, what type of SPICE model somebody mapped in a library, you can always remap it by just clicking on the part and clicking add model and changing the mapping. Your mapping from the library will be overridden by a mapping in a schematic. So that's all I'm going to say about that for now. I'll quickly go to, actually, let me just run a digital simulation really quickly to make sure we catch that, since we're probably running low on time now, excuse me. And then we'll go to get some questions. So we saw already some analog simulations, transient, AC, DC, operating point, and we saw all simulations that were using analog parts from the from the NGSpice Simulation library. We do have a new library that will be made public soon called NGSpice Digital, and as you can imagine, it has parts in it that have been mapped to digital models. So one thing that's new in Eagle, coming out soon, is digital simulation, in fact. And so this new library, which I'll show here real quick, I think I've already put it into use. So again, this library is not public right now, NGSpice-digital, but it will be very shortly, right after the next release coming soon. I have added it here because I have a local copy. So in this library, you see that there are a bunch of digital parts. So you see AND gates. I'll point to, here's just a buffer. This is a flip-flop, JK flip-flops, D flip-flops. We have NOR, NAND, OR, and XOR. We have a tri-state buffer. So a bunch of parts that you can use to create logic circuits. And in fact, of course, just like with analog, we have provided a bunch of examples along with, in addition to this library that has these parts. One thing to point out is this digital source part. We're going to look at that in a minute. That's really important to be able to provide stimulus for your digital circuits. And this part in particular works a little bit different than other parts. What I'm going to do just to let you see the digital capabilities here. I have this. I'm just going to go in and out of a couple modules here, Eagle modules, in a hierarchical schematic. So what I've done here is, at a high level, created this schematic that has this one module called add4. It has this block here. This is the digital source part. It's called X source. This is our input to our circuit, and this is another input called C in. This represents carry in. What we're doing here is we're creating two binary numbers, A0 through A3, B0 through B3, two 4-bit numbers, and we're going to use this block called add to actually add or subtract them. As you can see in the comments, it's an adder or subtractor circuit. This mode input is the selector of what is, of the mode, is it add or subtract. The outputs are this S0 through S3. Those are the results of adding A and B. The result is S. There's a carry out, and there are also some of the intermediate carry steps provided out just for clarity and for educational purposes. So essentially, I have two 4-bit binary numbers, and I'm going to add or subtract them in different ways and with different numbers. So I've set up a whole bunch of input here that we'll take a look at in a second. Very quickly, I'm going to right-click on this module. I'm going to click Edit Module. That allows us to essentially go into that part. This is an Eagle module. When I go into that adder part, you'll see that this is another circuit. Now, it's made up of a bunch of those digital parts, and there are some more module parts. These are, in fact, 1-bit adders created as hierarchical modules. I'm going to now zoom in on this part, right-click, and go to Edit Module. Here's really where this whole example starts. This is a 1-bit adder circuit. It's a very basic digital simulation example, or sorry, digital circuit example, and it's something that probably many of you are familiar with. Essentially, these parts can add 2 bits and produce a carry if the arithmetic results in a carry. So input is A and B, and carry in case you have a carry in from a previous stage. If you remember back to doing math by hand. And the output is S, and we have a carry out. So this circuit I put into a block here called add 1. I used 4 of those blocks, and with a couple other circuits here, these triangles are just buffers, so they're not really doing anything. Well, they have a purpose, but for the addition and subtraction, they're not doing anything special. I have this mode coming in. You'll see up here A0 through A3 and B0 through B3. Those are our binary numbers. They're being directed into these 1-bit adders, and this whole thing is then a 4-bit adder. Sorry, a little bit of zooming going on here. This whole circuit here is a 4-bit adder with two 4-bit numbers coming in, and it's noted here that when M is 0, it's an addition. When M is 1, it's a subtraction. And this whole thing here, I go back up again to our high-level schematic, was put into a hierarchical module, and so it's just shown as one block here. So we want to simulate adding these numbers. We want to see the output, and so now this brings us to our digital source part. When you place this part in your schematic, first thing you want to do is actually connect it to whatever it should be connected to, and I'm referring to this part here. This is one of the digital sources, and you click on it and right-click on it and choose Digital Source Setup. This is similar to the analog source setup with the other voltage source or the other examples. Digital source setup is a special command that runs on these parts that are specially set up to be digital sources. We can answer more questions about what that means later, but for now, let's just say that it means that it's mapped to a splice model of a specific type and in a specific way. And it is available in the NGSpice digital library, which you could just grab and place. And when you place those in your schematic and you right click and you start up digital source setup, you get essentially this table interface. You can load a digital value for each of the outputs of that part. So this was an 8 output digital source part. So there are 8 signals here, and there's also a column for time. You can set up your digital values in this way manually in this table, or you can load a similarly formatted CSV file that has the same, similar information. The number of columns will be checked. So you need a time column, and you need 1 column for every output on the digital source. So in this case, you can see a bunch of values, A and B, zeros and ones for the digital values were set up, and you click Save Setup, and then it will set up the source for you. I'm going to now go to simulate this circuit. We're actually ready. This is actually built from all parts that are already ready for simulation, but we've already gone through the conversion process. So if you have converted your parts, or if you are using parts that are already converted, the next thing you would do is essentially just simulate. I'm going to run a time simulation from 0 to 60 milliseconds. And as I noted before, I have a bunch of stuff already probed. So I have the digital values A and B. I have my outputs, and basically all the inputs and outputs are probed in this example. So we'll go here. We see that it's a different type of plot. We basically stack all of the digital signals on top of each other, so they're easy to see, easy to point out where's a 0 or a 1. For example, I'm looking at now, this is VC1, this is signal C1, and you can see that here it's 0 and here it's 1. Of course, in the legend on the right, I also see the actual values printed out in case it's not, sometimes if it's all 0, like in this case, this one B3, it's 0 throughout this whole time. So it's, it may not be easy to see the value. So just move your mouse. As you move, it'll show the value on the legend. In fact, it will also show you the values in your schematic as you move along. So in this case, let's just go to see the result real quick. MD is mode. Remember that 0, when it was 0, it's an addition. So I'm going to look at this portion right here. So if I look at the values, I see, well, let's look at, let's say this one. So I'm looking at this point in time. I'm just going to point out here. So I have a value here for A, I have a value here for B. The addition, let's see, this is 8, 9, 10, and the B is 0, 0, 1, 0, so that's 2. So the result of 10 plus 2 is 12, which is 1, 1, 0, 0. So the addition is correct, the circuit is working. I'm actually going to just stop there for that example. I'm going to mention really quick, there are a couple other examples. Others using, this one uses modules. It also uses a bunch of flip-flops to create a counter circuit. And that counter circuit is used to create the inputs for this addition. Similar circuit at the high level, but I'm using a counter to create our binary values. Same thing, I won't simulate that one. There's another example just to point out quickly. It's called mixed, and this shows you how you can connect analog and digital circuits. Similar to the digital examples, you have flip-flops and other digital gates, but on the left-hand side here, we have an op-amp circuit. So this is completely an analog circuit. The interface between the two is a part called A to D, and that lets you interface an analog circuit to a digital circuit. Otherwise, you'll get ERC errors if you connect analog and digital circuits together without using the interfacing part. There is a D to A part as well, which will let you take a digital signal and convert it to analog In this case, I'm taking a digital signal called and I'm converting it to analog and putting it through a capacitor. Excuse me. So we're like probably way over time. So I'm going to recap a little bit. We went through analog simulations, and okay, simulation in general with Eagle. We started with analog simulations, and we went through a bunch of examples. Some using SPICE model files, subcircuit files. Some using model cards like the diode that we looked at. Some components that didn't require any model files at all. But we simulated successfully transient simulations, simulations over frequency. Actually, I don't think we did a simulation over frequency. I'll just run one in the background while I'm talking here. And we also went through a DC simulation. Oh yeah, we did do an AC simulation. So, and we also did a DC simulation, which showed us, if you remember, the FET characterization example allowed us to vary the voltage value from 0 to 10 volts as we looked at the current through a transistor. And we looked at an operating point simulation. We talked a little bit about probes, but not too much in depth. We'll check for questions in a second. And then we went into digital simulation. I mentioned that there are libraries available. NGSpice Simulation has all the analog stuff. NGSpice Digital will be available soon and has a bunch of digital parts. Those libraries are good examples of how you should map parts, and what models look like and what type of models are needed for what type of parts. So it's a good all around. They're good reference for you to make your own circuits. We also took a schematic called Convert, which ships with Eagle, and we converted that circuit to be simulation ready using the add model command and the related interface and dialogues. and that's an example of how you take any schematic, your schematic, for your new great hardware device, how to take that schematic and convert it so that it's simulatable. Note that the conversion mapping process does not change your schematic. It doesn't hurt your board design. In fact, it does nothing to the board design. All it does is add some information for simulation. So when I say convert, I mean convert to be simulation ready. I do not mean anything else, meaning converting it or changing your schematic to something that's no longer useful. Conversion in this context means making it SPICE ready. So maybe with that, let me let Jorge make a couple comments here. I'm sure there are questions. Jorge, do you want me to address anything in particular?
Yes, we do have one question that has come in. You can hear me, Ed? Can you hear me good? Yeah, we have a question from Tamas, and he's asking, is it possible to do math with the waveform? So like, for example, you have a voltage waveform and divide it by current to get an impedance waveform.
Right. I think there is probably a way in terms of adding those values to. Sorry, I'm not sure. I heard a weird sound. Okay, maybe somebody just dropped off. I think there's a way to do it, using an expression in a value of a part. For example, there's a certain part called an arbitrary source where you can actually put in expressions on the plot itself. I understand that's where the question is. I think we do not have that yet, but we certainly will look into adding that soon. And I know exactly what you're talking about. It will be coming soon. Let's just leave it at that.
Okay, awesome. Thomas, if that answers the question, just let us know. Wanted to add a comment about when you're doing an AC sweep and you pick 1 volt. As I mentioned, it makes the scaling easier. The other benefit is when you pick 1 volt, you're basically graphing the transfer function of the circuit, because as we know, transfer function is V out over V in. If V in is 1, having a plot of V out is the plot of the transfer function. So that's the other reason that we recommend to use 1 whenever you're doing that type of simulation.
Yep, that's a good point. And I'm just running this op-amp example, and I'll put an example here where we're looking at V out. Let's say V out 2, and I want to look at the phase of V out 2. So this is a special type of plot that many are probably familiar with, and I just wanted to point it out. So phase is in degrees, it's on the right side. And the voltage is using the left side y-axis, and this is in dB. So if we might look at what the transfer function looks like, or what the gain is, or what a voltage is at a certain frequency, and we also want to see the phase. We just wanted to point that out.
Cool. Any other questions? That was the only question that I saw come in.
Okay.
Yeah. Looks like there's nothing else right now. If anything pops up, I'll interrupt you, Ed.
Okay. Yeah, and I would add there are certainly a lot of little details here and there. Hopefully I covered all the basics and the basis for for general use. But there are certainly more advanced features and things you can do with parts, and different tricks you can do. And I guess I would add that soon we'll have some more resources in terms of videos on some of those advanced topics. So just wanted to put that out there. Some may be wondering, for example, if you have like an IC that has, let's say, 4 op amps in the device, how do you map that? This type of thing. There are examples. There's one called Map Gates that addresses that specific task. But otherwise, and again, mentioning, we'll have some more advanced usage videos coming out soon.
Okay. So, Ed, if there's nothing else, I think we can end it here.
All right. Well, thanks everyone. As always, the forum is a great place. It's to get answers on your questions. So feel free. We're all on there, and we all are contributing. So any questions you have, we'll get right to it. I see a question here on the A to D and D to A parts. Can you set the thresholds? So I think there are thresholds set for the for some of the parts that ship with the library. Offhand, I don't recall at this minute. So about those parts, but we can take a look. I believe that those parts are directly mapped to some built-in parts with for the NGSpice simulator. So however those work, there will be certainly a lot more detail in the NGSpice manual. I don't recall offhand the threshold. There are some parts that have thresholds set. For example, I thought some of the, I'm not going to guess. Some of the parts have thresholds set, some do not. And I'm not sure about that one. You can, of course, create your own A to D and D to A parts and set your own thresholds, but those are directly mapped to parts that are intrinsic to the NGSpice install that comes with Eagle. So I'm not sure, and the answer is that if there are, I don't believe they're configurable in those cases for those specific parts.
Okay. Excellent. Okay.
Yeah, and as there are needs for other parts that are useful to you, or other types of parts or things like that, like the threshold question, that's a really good one for the forum. And please post there, and we'll take a look and make adjustments as necessary or if applicable. Thanks everyone. We went way over time, and thanks for staying on. I guess that's about it.
Okay, bye everyone. Have a great day.